Let us see columns. A column or a strut is defined as a member of a structure which is subjected to an axial compressive load. When a structure is vertical and subjected to an axial compressive load, we call it as a column. When the structure is inclined at some position other than 90 degrees, we call it as a strut. This we need to remember. If a member, this is what repeated here, if member of a structure is vertical and both ends are fixed rigidly while subjected to axial compressive load, the member is known as a column. Example is given as vertical pillar. So if a member of a structure is not vertical and one or both ends are hinged while subjected to an axial compressive load, the member is known as a strut. Example, connecting rod, piston rods, etc. It's given. The failure of the column takes place due to any one of the following stresses set up in the columns, like, for example, direct compressive stresses, buckling stresses, and combined direct compressive and buckling stresses. We'll see in detail. Failure of a short column. Okay, failure of a short column. How the failure takes place for a short column. Let us take a column, short column, subjected to an axial compressive load. It can be of any cross section. Here I've taken rectangle or square, whatever it is. So it can be of any cross section, but short column. So here, compressive load divided by cross section area gives you the compressive stress. When you keep on increase the load P, at some instant, the member will cause to crush. The member will cause to crush. So I can call that load as a crushing load divided by cross-sectional area. We call it as a crushing stress. We call it as a crushing stress. So hence all short columns fails due to crushing. This is the conclusion. All short columns fail due to crushing. When you go to the long columns, failure of a long column, let us take a long column subjected to an axial compressive load. Okay. So when we apply a load P, for example, if nothing is happening to my column, means I can call that P as a safe load. Okay, I can call it as a safe load or a safe compressive load, something like that. Okay. So we are applying a load. So the column undergoes a lateral deflection. You can see here the lateral deflection, let it be delta or whatever it is. Okay. So long columns do not fail by crushing alone. Okay, crushing alone, but also by bending, which is known as a buckling. So this long column subjected to crushing as well as the bending. So the load at which the column just buckles or bends is known as a buckling load or critical load or crippling load or collapsing load, like that. We can give different names for that. So in long columns, the direct compressive stresses are negligible as compared to buckling stresses. Hence, very long columns are subjected to buckling stresses only. So we come to conclusion, failure of a long column are due to buckling stresses only, whereas short columns due to crushing. Please, you do remember this. The assumptions. For example, now if I want to find out the critical load, crippling load, or collapsing load, whatever it is, for a column, we need to determine or derive the expression or a formula to find the crippling load or a critical load. Okay, so we need to follow certain assumptions. Okay, so the Euler made some assumptions in his Euler's column theory. So the column is initially perfectly straight and the load is applied axially. The cross section of the column is uniform throughout its length. The column material is perfectly elastic, homogeneous, And isotropic also obeys Hooke's law. That means within the elastic limit. We are not going beyond that. So the length of the column is very small as compared to its lateral dimensions. The length of the column, very large, length of the column is very large when compared to its lateral dimensions, that is cross-sectional dimensions. The direct stress is very small as compared to the bending stress. The direct stress is nothing but load by area or compressive stress divided by cross-sectional area. I call it as a direct compressive stress. So bending stress is something different, which you get from the solid mechanics. M by I is equal to sigma B by Y. Sigma B is equal to M by I into Y, or M by Z, where Z is the section modulus. That is nothing but a bending stress. The column will fail by buckling alone. We assume that column fails only by buckling. The self-weight of the column is neglected or negligible. So we are not considering the weight of the column during our calculation. We take or we consider only the external load, that is axial compressive load, that are applied to our column. Okay, we are not considering the weight. Self-weight of the column is neglected. End conditions, that is support conditions. What are the different support conditions we have for long columns? Both the ends are hinged or pinned. Okay, hinged support or pinned support. One end is fixed and other end will be free. Both the ends of the column are fixed or clamped or built in. One end is fixed, other end is hinged or pinned. So these are the four different end conditions that we are going to see in this Euler's column theory. Okay, we are going to derive the Euler's formula or Euler's critical load formula, whatever it is. So we need to understand the certain boundary conditions that you might have learned in a deflection of beams, whether it's a deflection in simply supported beam or a deflection in cantilever beam. Certain end conditions which we would have followed for determining the constant of integration in the case of a double integration method. That is, at the hinged end or at the hinged support, deflection is 0. At the fixed end support, both slope and deflection are 0. And at the free end, deflection is not 0. So all these things we need to remember in our mind while deriving the expression, because we may have to integrate and get the constant of integration by remembering these boundary conditions. Sign conventions, which is very, very important. The sign conventions which we need to follow while writing the bending moment expression. Now you can see here the picture A, the left-hand side, when it is subjected to an axial compressive load, it produces convexity. You can see if this is the direction of bending, means we take that bending moment to be positive. We call it as a positive bending moment. And in the figure B, it shows negative when the column bends like this, which undergoes concavity shape. So we call it as a negative bending moment. Okay, negative bending moment. These sign conventions we have to remember while writing the bending moment equation. Now let us determine the why we are saying like bending moment, why we have to consider the sign convention while taking bending moment, why we have to take bending moment. If you look at the expression from the what you call the deflection, that is M by I is equal to E by R. Okay, so M is equal to EI by R, so which can be written as EI into D square Y by DX square. So I am going to write down the bending moment expression. M is equal to EI D square Y by DX square is equal to, we will write down the bending moment expression. Then I will integrate D square Y by DX square to get the slope equation dy by dx. Again, we will integrate to get the deflection equation. Then we apply the boundary conditions to determine the constant of integration. Then to arrive the final Euler's formula or critical load or crippling load formula for a particular end condition. Now let us see the expression for crippling load or critical load when both the ends of the column are hinged, when both the ends of the column are hinged or pinned. So we have a support here. Okay, we have a support here. So all these things are available in the textbooks by strength of material textbook, any textbook. Okay, or Eskurmi or Bansal, whatever it is. So I have taken a column here, the AB of length L. Okay, where it is subjected to an axial compressive load P. So due to this application of load, the column undergoes the lateral buckling or lateral bending. And let us consider a section at C, for example, at a distance x from the bottom end. Let y be the deflection at C. Let y be the deflection at C or at the considered section XX. At the considered section XX. So moment. So we call M is equal to EI d square y by dx square. So this is giving negative bending moment. You can see here the sign convention. So minus, I'm taking moment with respect to C. So P force into perpendicular distance y, P into y. So d square y by dx square plus P by EI is equal to 0. I have taken this minus P to the left hand side, dividing by EI throughout, you get d square y by dx square plus P by EI into y is equal to 0. So this is a partial differential equation or differential equation for which we have to find out like y is equal to CF plus PI. That is a complementary function plus particular integral that we need to find out. So we need to find out the solution of the above differential equation is y is equal to C1 cos of x root of P by EI plus C2 into sine of x into root of P by EI. So I can call this as a general solution for the above differential equation, Okay. So C1 and C2 are the constants of integration. Okay, so let us take that equation again. So at A, that is initial support, x is equal to 0, deflection is 0. This is the boundary condition. So when you just apply it, we get from this equation C1 to be 0 because x is 0, right? So cos 0 is 1. So y is 0. So C1 is 0. At B, x is equal to L. Y is equal to 0. So from the same equation, okay, y is 0, C1 already 0, this term will get vanished, C2 into sine of L root of P by EI. Now C2, if you take here, sine of L P by EI is equal to 0, sine 0 is 0, sine 180 is 0, like this we can write up the equation. But C2 cannot be equal to 0, that we need to remember. Okay, if both C1 and C2 are 0 means y, deflection y will be 0. Okay, which is not correct. So sine of L root of P by EI is equal to 0. That's why we are equating this to 0. So we take the first practical value into consideration, that is sine of L root of P by EI is equal to sine pi. So that finally we arrive the equation like this, L into root of P by EI is equal to pi, Okay, so taking the least practical value, we take this, then squaring on both sides, we get P is equal to pi square EI by L square. P is equal to pi square EI by L square, which is nothing but the critical load or crippling load or Euler's formula or Euler's load for a column having both ends hinged or pinned. Now the expression for crippling load when one end of the column is fixed and the other end is free. Now here you can see the bottom end EA is fixed and the top B is free. Okay, so once when the load is supplied, axial compressive load is supplied at the free end, it deflects to an amount of A. Okay, A. L is the length of the column. So we consider some section at a distance X. At the considered section Y, small letter y is the deflection. Okay, small letter y is the deflection. Now moment, as we told earlier, m is equal to ei d square y by dx square. So now I need to take a moment. Okay, I have to take a moment with respect to this point. So this is a positive bending moment, produces a positive bending moment. Okay, so I'm taking moment with respect to this. So I need this distance. I need this distance. This is A and this is Y. So this distance will be A minus Y. This distance will be A minus Y. Okay. So that's why P into A minus Y. This is the moment equation. Let us rearrange it and divide by EI. Okay, so after rearranging it, dividing it by EI, we get the expression like this. Now, the general solution for this differential equation, for example, whenever you get the right hand side term to be 0, just for simplicity of understanding, I'm saying, otherwise you have to calculate y is equal to CF plus PI, like finding the complementary function plus particular integral, everything. So instead of doing all those things, when the right hand side term is 0 means we have got the general solution to be y is equal to C1 cos of x root of P by EI plus C2 sine of x root of P by EI. Okay. Now in this, whenever you get a right hand side term, you just divide by P by EI or multiply by EI by P. Remaining term, whatever you're getting, simply add the existing expression, which we have written by considering the right hand side to be 0. Okay. So when I multiply this right hand side term to by EI by P, left out term is A. Simply plus A. Now this is the valid general solution for the above differential equation. So as C1 and C2 are the constants of integration. So we are just differentiating this with respect to x. Why I'm differentiating means at the fixed end, we get both slope and deflection to be 0. So I will be considering the slope also. So in order to get the slope equation, I'm differentiating the deflection equation. So dy by dx is equal to cos differentiation is minus sine. Okay, so that is why we are getting minus sine of x root of P by EI, and differentiation of this is root of P by EI plus C2 sine differentiated to cos of this differentiation bracket you get into root of P by ER plus A is a constant, so 0. So after simplification, you get this. Then write down again the equation. Y is equal to the deflection. At A, x is 0, y is 0. Substitute this equation. At A, x is 0, y is 0. So what will happen? C1 is equal to minus A. So this term will get vanished, sine term. Because sine 0 is 0, y is 0, cos 0 is 1. So C1 is equal to minus A. At A, x is equal to 0, slope is also 0. The slope expression you substitute dy by dx to be 0. Okay, sine 0 is 0. And C2 is C2, cos 0 is 1. Okay, sine 0 is 0 here. C1 is minus A. Okay. So here in this, either C2 or root of P by EI is equal to 0. But here root of P by EI cannot be equal to 0 because we are adding a load. This made up of some material, column is made up of some material. Definitely will have a Young's modulus, and it has got certain cross section. Area moment of inertia will be there. So root of P by EI cannot be equal to 0, but C2 can be equal to 0. Okay, so by considering this and plugging into the deflection equation, we get y is equal to C1 is minus A cos of x into root of P by EI plus A. Okay, C2 is 0. So at the free end of the column, that is where x is equal to L, deflection y is equal to A. Substitute in the above equation, y is nothing but A, okay, cos of L. Okay, so this A and this A will get cancelled, okay. So when you take it to the other side or multiply by minus, you will get plus A into cos of L root of P by EI. But A cannot be equal to 0 because we are having initial deflection as it is a free end and subject to end load. But cos of L root of P by EI is equal to 0. So cos 90, let us consider the least practical value, cos pi by 2. Okay, so L into root of P by EI is equal to pi by 2. So squaring on either side, you get P critical is equal to pi square EI by 4L square. Pi square EI by 4L square is the critical load formula for a column whose one end is fixed, other end is free.